Hi, Stu Schwartz from MasterMathMentor.com. This is video AB26. The topic is u-substitution and it covers the AB manual pages 158 through 160. Suppose we were asked to integrate x times the quantity x squared minus 1 quantity squared dx. This presents no problem. We can expand the expression to get x to the fifth minus 2x to the third plus x. And now we can integrate that expression dx to get x to the sixth over 6 minus x to the fourth over 2 plus x squared over 2 plus c. But how about the integral of x times the quantity x squared minus 1 to the fifth power dx? Do we really want to multiply that expression out? There has to be a better way, and there is. We call this method u-substitution. We start by defining an expression called u, which will usually be the expression in parentheses. So we're going to let u equal x squared minus 1. Now, the next step may seem strange. Even though we're doing integration, we are going to find du dx. And we find that du dx equals 2x. We will then cross multiply to get du is equal to 2x dx. The next step is the key. We now need to rewrite the integral of x times x squared minus 1 to the fifth power dx in terms of u. To do this, we need to manufacture a 2x dx. We have the x dx, but we need a 2. So we're going to multiply our integral by 2 on the inside and 1/2 on the outside, which we know is the same thing as multiplying by 1. So the integral of x quantity x squared minus 1 to the fifth dx is now 1/2 the integral of 2x x squared minus 1 to the fifth dx. Our next step will write everything in terms of u and then integrate in terms of u. So this problem becomes 1/2 the integral of u to the fifth du. Remember, du, as we've seen above, is 2x dx. So when we integrate this expression, we get 1/2 u to the sixth over 6, which is u to the sixth over 12. Finally, we have to change everything back to x. So we will do so and add on our constant, and our final answer is quantity x squared minus 1 to the sixth power over 12 plus c. When students first learn this technique, it is always good to check work. So if we take the derivative of our answer, x squared minus 1 to the sixth power over 12 plus c, we end up getting 6 times x squared minus 1 to the fifth power times 2x all over 12. The 6 and 2 cancels the 12, and we are back to x quantity x squared minus 1 to the fifth power. The only way to get good at this is to do problem after problem. So here are 18 problems that will show all different variations on the same theme. Number 1 reads the integral of quantity 3x minus 2 to the fourth dx. I like to work in 2 columns. I like to show my u-substitution on the right-hand side and the bulk of the problem on the left. So I will make u equal to 3x minus 2, and therefore du dx equals 3, and du is equal to 3 dx. That means we need a 3 dx in the problem. We only have a dx in the problem, so we need a 3. So on the left side, notice I wrote the 3 on the inside compensated by 1/3 on the outside. So we have 1/3 the integral of 3 quantity 3x minus 2 to the fourth power dx. We can now write everything in terms of u. This becomes 1/3 u to the 4th du. Remember, the 3 dx is du. We can integrate that to get 1/3 u to the 5th over 5, and my final answer is 3x minus 2 to the 5th power over 15 plus c. You can take the derivative and show you will end up with quantity 3x minus 2 to the 4th power. Number 2 reads the integral of the square root of 5x plus 4 dx. We will let u equal 5x plus 4, therefore du dx equals 5, and du is equal to 5 dx. That means we need a 5 dx in the problem. We have the dx, we need a 5. So we put 5 on the inside, 1/5 on the outside. And this becomes 1/5 the integral of u to the 1/2 du, which becomes 1/5 u to the 3/2 divided by 3/2, which is the same as multiplying by 2/3. And the final answer is 2 times the quantity 5x plus 4 to the 3/2 power over 15 plus c. Again, take the derivative to show that when you do so, you will get the square root of 5x plus 4. 3 reads the integral of 4, quantity 6x minus 1 to the 2/3 power dx. U is equal to 6x minus 1, du dx is equal to 6, and therefore du is equal to 6 dx. We need a 6, so we will put it on the inside. I also took the 4 to the outside and now divide it by 6. So this becomes 2/3 the integral of u to the 2/3 du, which is 2/3 u to the 5/3 divided by 5/3. Final answer will be 2 quantity 6x plus 1 to the 5/3 all over 5 plus c. It is very important when you do this problem to show your work. Do not do too many steps in your head. Somebody's going to have to read it. If you refer to a u, you better write down what u represents. Number 4 reads the integral of x square root of x squared minus 2 dx. We will let u equal x squared minus 2, therefore du dx equals 2x, and du is equal to 2x dx. We have the x dx, we need a 2. So we put the 2 to the inside and 1/2 to the outside. This becomes 1/2 u to the 1/2 du. Students sometimes get confused with this step. They say, what happened to the 2x and the dx? That all got eaten up by du. So this becomes 1/2 u to the 3/2 divided by 3/2, and my final answer is x squared minus 2 to the 3/2 over 3 plus c. In number 5, we have the integral of x squared times the square root of 1 minus 4x cubed dx. Our u is equal to 1 minus 4x cubed, and our du is equal to negative 12x squared dx. We have the x squared dx. We're missing a negative 12. So we put a negative 12 on the inside of the integral and a negative 1/12 on the outside of the integral. So this becomes negative 1/12 the integral of u to the 1/2 du. That becomes negative 1/12 u to the 3/2 divided by 3/2, which is multiplying by 2/3. Final answer, negative quantity 1 minus 4x to the 3rd raised to the 3/2 power all over 18 plus c. In number 6, we have the integral of x over the cubed root of 2x squared minus 1 dx. We will let u equal 2x squared minus 1, and du is equal to 4x dx. Notice again, we are no longer writing du dx. We can just go immediately to du. So we need a 4x dx in our problem. We have the x and dx, we're missing a 4. So we put 4 to the inside, 1/4 to the outside. So this problem becomes 1/4 the integral of u to the negative 1/3 du, which is 1/4 times u to the 2/3 divided by 2/3, which is multiplying by 3/2. So our final answer is 3 quantity 2x squared minus 1 to the 2/3 power all over 8 plus c. Let's review two problems in a little bit more depth. First, number 1, the integral of 3x minus 2 quantity to the 4th dx. We started it with u equal to 3x minus 2, du dx is equal to 3, and therefore du is equal to 3 dx. Our school of thought was that we needed 3 dx into the problem, so we multiplied by 3 on the inside and multiplied by 1/3 on the outside. But here's another approach. You could solve for dx. Dx is equal to du over 3. So we go to the original expression, and wherever we see a dx, we replace it with a du over 3. We can take the division by 3 to the outside and write this problem in terms of u. This becomes 1/3 the integral of u to the 4th du, and we are right back to where we started. We end up with the same answer, 3x minus 2 to the 5th over 15 plus c. It's a matter of approach. The way I originally taught it asks, what do we need to integrate the expression? This technique actually solves for dx, and you don't have to ask yourself that question. Both methods are taught. I was taught the first way, and that's why I teach it like that. Many teachers teach it this way. Doesn't matter which way you do it, you will get the same answer. I find that for some reason students learn it better the first way, and I will continue with that method. Number 4, I changed the problem to the integral of the square root of x squared minus 2 rather than the integral of x times the square root of x squared minus 2 dx. Our approach is the same. We let u equal to x squared minus 2, du dx is equal to 2x, and therefore du is equal to 2x dx. We do not have a 2x in our problem, so we manufacture it, multiplying by 2x on the inside, dividing by 2x on the outside. This becomes 1 over 2x, the integral of u to the 1/2 du, and that becomes 1 over 2x times u to the 3/2 divided by 3/2. And our final answer is x squared minus 2 to the 3/2 power over 3x plus c. It looks good, but wrong, wrong, wrong. You cannot do this. You cannot multiply the inside and outside of an integral by a variable, only a constant. So while we can multiply the inside and outside by 2 and 1/2, we cannot do it with 2x and 1 over 2x. The reason should be clear. If we attempt to take the derivative of our answer, you see the results below. We get x squared minus 2 to the 3/2 over 3x plus c. We'd like to take the derivative of that. We end up getting 1/3, and by the quotient rule, we get 3/2 x squared minus 2 to the 1/2 times 2x, minus x squared minus 2 to the 3/2 power all over x squared. I don't have to do any more simplification to realize that this is not going to be the square root of x squared minus 2. So you may only work the inside and outside with constants, never variables. By the way, that does not mean that the square root of x squared minus 2 cannot be integrated. It just means it cannot be integrated using u-substitution. It turns out that the integral of the square root of x squared minus 2 dx is the complicated expression x times the square root of x squared minus 2 over 2 minus the natural log of the square root of x squared minus 2 plus x. You may want to take the derivative of that expression and show that that will give you x squared, the square root of x squared minus 2. Numbers 7 through 12 are more problems in taking indefinite integrals. They're a little bit more difficult and also involve trig. Number 7 asks the integral of x to the 1/2 times the quantity x to the 3/2 plus 4 raised to the 9th power dx. U will be x to the 3/2 plus 4, and du will be 3/2 x to the 1/2. We have the x to the 1/2. We need the 3/2. So we multiply by 3/2 on the inside and 2/3 on the outside. So this becomes 2/3 the integral of u to the 9th du, which is 2/3 u to the 10th over 10, and the final answer is x to the 3/2 plus 4, quantity to the 10th power, over 15 plus c. 8 reads the integral of quantity x plus 2 times the square root of x squared plus 4x minus 5. In this case, there are two expressions in parentheses. Usually in that case, u is the more complicated expression, and in this case, u will be x squared plus 4x minus 5, and du is equal to quantity 2x plus 4 dx. We have an x plus 2, we need a 2x plus 4, so we multiply by 2 on the inside, 1/2 on the outside. So this becomes 1/2 the integral of u to the 1/2 du, which is 1/2 times u to the 3/2 divided by 3/2, or 2/3 u to the 3/2. Doing the cancellation and replacement of u, we get x squared plus 4x minus 5 raised to the 3/2 power over 3 plus c. 9 reads the integral of x minus the square root of 3x dx. This type of problem occurs quite a bit. We have to split it into two separate integrals. We can take the integral of x using our power rule, but we need to take the integral of quantity 3x to the 1/2 power using u-substitution. So the integral of x dx is x squared over 2, and the integral of the 3x raised to the 1/2 power has u as 3x. Du will be equal to 3 dx, and therefore this becomes 1/3 the integral of u to the 1/2 du. So we get x squared over 2 minus 1/3 times 2/3 u to the 3/2 power. And substituting, we get x squared over 2 minus 2/9 times the quantity 3x raised to the 3/2 power plus c. Number 10 asks for the integral of the square root of x squared minus 1 dx. We let u equal to x squared minus 1, du is equal to 2x dx. And we conclude, as we saw before, that we cannot integrate this because we cannot pull off the 2x. We can put a 2 on the inside and a 1/2 on the outside, but variables are not allowed. So therefore, this integral cannot be taken by u-substitution. Number 11 reads the integral of cosine of 4x dx. Sometimes it's helpful to put a parenthesis around the 4x. U in this case will be 4x and du will be 4 dx. So we can create what we need by putting a 4 to the inside and a 1/4 to the outside. And this becomes 1/4 the integral of cosine u du, which we know is 1/4 sine u. Final answer, sine of 4x over 4 plus c. Again, taking the derivative of this, we get cosine of 4x over 4 times 4, and that gives us cosine of 4x. Number 12 reads the integral of 3 sine of 1 minus 3x dx. U is 1 minus 3x, du is negative 3 dx. We have the 3, we have the dx, we're just missing a negative sign. So we put a negative on the inside and a negative on the outside. And this problem becomes negative the integral of sine u du. And the integral of sine is negative cosine, so this problem becomes cosine of u. Final answer, cosine of quantity 1 minus 3x plus c. Taking the derivative of that, we get negative sine of 1 minus 3x times negative 3. The negatives cancel and we're left with 3 sine of 1 minus 3x, where we started. Problems 13 through 18 are even tougher problems with u-substitution. 13 reads the integral of sine cubed of x, cosine of x, dx. Problems like this, it's good to write them with parentheses. So this becomes the integral of sine of x cubed, cosine of x, dx. You have a choice. U could either be sine of x or cosine of x. If u is cosine of x, du is negative sine of x dx. But we have a sine of x cubed. That won't work. So we will let u equal sine of x, and du is equal to cosine of x dx. And we have it. So nothing needs to be done. This integral simply is the integral of u to the third du, which is u to the fourth over 4, or sine to the fourth of x over 4 plus c. Confirm your answer by taking the derivative. We get 4 times sine cubed of x over 4 times cosine of x, which is sine cubed of x cosine of x. Right back where we started. 14 reads the integral of cosine of x times the square root of 1 minus sine of x. So u will be 1 minus sine of x, and du will equal negative cosine of x dx. We have everything but the negative. So we put the negative to the inside and negative to the outside, and this becomes negative u to the 1/2 du, which is negative 2u to the 3/2 over 3. Final answer is negative 2 times the quantity 1 minus sine of x raised to the 3/2 all over 3 plus c. Problems 15 and 16 are similar, but done very differently. Number 15 reads the integral of tangent of 10x, secant of 10x, dx. In order to do this, you must realize that tangent secant is one of your basic integration forms. So we let u equal 10x, therefore du is equal to 10 dx. We need a 10 on the inside, so we multiply by 1/10 on the outside. So this problem becomes 1/10 the integral of tangent u, secant u, du. And our integration becomes 1/10 of secant u. So the final answer is 1/10 the secant of 10x plus c. Number 16 reads the integral of tangent squared of x, secant squared of x, dx. It looks similar to 15 in that there's a tangent and a secant. But this is different. We will rewrite the problem as tangent of x squared, secant squared of x, dx. So if u is tangent of x, du is secant squared of x dx, which we have in the problem. So no work needs to be done to change this to u's. This is simply the integral of u squared du. And that integration turns out to be u cubed over 3. Final answer, tangent of x cubed over 3 plus c. If we were to take the derivative of this, we would get 3 times tangent of x squared over 3 times the derivative of tangent, which is secant squared. And we are right back to where we started from. Look at the difference between 15 and 16 carefully. You will encounter problems like that on the AP exam. 17 and 18 show how tricky integration can be, and sometimes you think it can't be done, and it can. In 17, we have the integral of x plus 2 times the square root of x minus 4. We let u equal x minus 4, and du is equal to dx. However, we have this x plus 2 that we can't get rid of. And at first glance, you think, well, there's nothing we can do. However, if I solve for x, we get, since u is equal to x minus 4, x equals u plus 4. So I am now going to replace x with u plus 4 in the original expression. And this becomes the integral of u plus 4 plus 2 times u to the 1/2 du. So we now have an expression, the integral of u to the 3/2 plus 6u to the 1/2. And we can integrate that in terms of u. So this becomes 2/5 u to the 5/2 plus 6 times 2/3 u to the 3/2. We now replace the u with x minus 4, and our final answer is 2/5 times x minus 4 to the 5/2 power plus 4 times x minus 4 to the 3/2 power plus c. I leave it to you to take the derivative and show that we will come right back to quantity x plus 2 square root x minus 4. 18 is trickier yet. The integral of x squared over the square root of x minus 1 dx. We will bring the square root of x minus 1 upstairs and write that as x minus 1 to the 1/2 power. And I will let u equal x minus 1. Du dx is equal to 1, so du is equal to dx. And therefore x is equal to u plus 1. So I'm going to replace in the original expression every x with a u plus 1. So this becomes the integral of u plus 1 quantity squared, u to the negative 1/2 du. Expanding, we end up with u to the 3/2 plus 2u to the 1/2 plus u to the negative 1/2 du. We integrate and get 2/5 u to the 5/2 plus 2 times 2/3 u to the 3/2 plus 2u to the 1/2. And our final answer is 2/5 x minus 1 to the 5/2 power plus 4/3 x minus 1 to the 3/2 power plus 2 x minus 1 to the 1/2 power plus c. Again, you may want to take the derivative of this and show that you will come right back to x squared over the square root of x minus 1.